So,
Go ahead and stand over in the middle there.
um, so I guess my question was, let's see, what happens to snow after it falls on the ground during a relatively warm period near 0 degrees Celsius? And so I'd like to present this as a question of what can we see about the ground conditions of snow between snowfall events. And so basically this morning I had to rush and do the lab, and I had the fortune of doing it in the darkness and underneath a street lamp, which actually served the purpose of illuminating the snow from the top down. So looking at recent snowfall events, I could see that there were very small striated horizontal bands, and they seem to vary in density between light and darker bands. And so by looking at the crystals and the granulars, I could see that the darker bands were consisting of denser snow. And so if each band represented a independent snowfall event, then the characteristics of that band being more dense was most likely a product of the ground conditions at the time of the snowfall and until the next one. And so I concluded that the darker bands were probably created during warmer periods, during and between the next snowfall event. And so I think by further exploring the characteristics of snowfall at lower temperatures than 0 degrees and at higher temperatures, then we could conclude more accurately what those layers would be representative of. Thank you.
Any questions for him?
Any questions?
Okay. Yeah, I would like in the future, we didn't talk about this beforehand, but for future presentations, and we don't have to do this much today, but it is nice to have, for you guys to be thinking about some questions to ask afterwards. But I think we won't pressure you guys too much today since we didn't go through. There's a lot of, this is still just sort of first impressions on what snow is like. So thank you for being the first one to get up. Who wants to go next?
I can go next.
Okay.
Are you ready?
Sure. You have to tilt this way back because you're taller.
Yeah, okay, so my question is kind of similar. It's what happens to the snow after it falls on the ground during a colder period, below 10 degrees Celsius. So we had really conditions like that actually last Thursday, because it was about 11 below, 11.5 something, and it was actually light snow. So back in Norway, or at least where I'm from, I'm used to it never snowing and that cold temperatures. So I get that's kind of an interior phenomenon that happens here. But yeah, the key points is that when it's colder, the metamorphism of the snow goes slower, so it just takes more time for the snow to settle. So basically, the snow that falls is the same, or like when it's snowing, like it was last Thursday, the snow that fell was exactly the same to the snow that we observed on the ground, like the structure of it. And that was kind of small crystals when we took a picture of it. And they weren't like perfect snow crystals, but that's mostly to atmospheric influences, like it's mechanical wear on the snow crystals when they're falling down. Yeah, so I guess that's the key points. And also it's important to remember that it's not only the temperature that matters, it's also wind and the solar radiation, because the wind can like grind up the snow really fast and make it into much denser snow. And solar radiation can help, even though the temperature is low, it can have a melting effect. And also we actually did some density measurements, and we got it to be 260 grams per it's gram per cubic decimeter. So that's really high to be like, it's a dry snow as average of about 100. So it was a bit more moist than you would say. We would maybe call it completely dry snow. And also you could, if you squeeze it together, you could actually make snowballs of it, but it was not good snowball, but you can like try to do that. Yeah, I guess that's my main points.
Okay.
Thanks.
Yeah.
Any questions? Yeah.
So, was the snow that you were looking at predominantly towards the top of your pit, or are you talking about snow that was also maybe compressed?
I think that was. I have to check the question again. Yeah, so that was like the.
Just the very top.
Yeah, that's how I interpreted the question.
That was okay. Cool.
Yeah. So, oh, go ahead.
Okay. My question is, did you observe the edge of the snow? I know, I noticed sometimes, when it's cold, the edge of the snowflakes is more sharp, but when it's more warm, it's kind of round.
Yeah. They were really rounded. We didn't really find we took some samples of us and actually took photos of them, and we didn't find like the perfect 6-edge snow crystals. But I guess the temperature was warm for Fairbanks, but I guess I will think it's because of atmospheric, like mechanical wear on the snow crystals, that they get more rounded. So yeah.
Yeah. So in -10 is, we were out there right at kind of the boundary between what we might consider warm snow metamorphism and cold snow metamorphism. So, but you're right. So the crystals, if they fall, those dendritic, really beautiful crystals, and we talked about this a little bit on Thursday, but the shape of the snow crystal that falls from the atmosphere depends on the air temperature and the amount of moisture in the air. And those beautiful dendritic crystals, they fall when there's much higher moisture content in the air, at both warm and cold temperatures. But warm, like if it's -4, say, -3 or 4, so relatively warm, then you're more likely to get those beautiful dendritic crystals.
Is that because they grow in the atmosphere?
They grow the way they grow in the atmosphere, given the moisture available and the temperature they're growing at. They can also grow at like -15 or -20, again when the atmosphere is more has more humidity in it. There's a little chart in this book that shows the different shapes of the crystals based on the moisture content in the actual temperature. But after it falls in the ground, regardless of what shape it is when it falls, if it's warm, you're always going to get a little bit of rounding of the crystals. If it's cold, you won't. It'll go slower. They won't round out like that. And we were kind of right at the edge of that. So it was hard to really see that in one way or the other, because there were little tiny crystals that were falling. So we couldn't. It was really hard to even see those. But.
And also, I have a question. I remember, what's the name of the crystals hanging in the air? Like when two snowflakes get together and they grow bigger. That's the name of the hand something. I forgot.
Hand something.
Yeah, it's I went to a seminar last semester. The people did research on snow. He talks about the snow growing in the atmosphere, and there's a name for it.
There's a few different. There's
the book had a bunch of names for them.
Yeah, there's needles. There's the dendritic ones, which are the ones that we always draw pictures of. There's columns. There's capped columns.
Are they bouncy?
It's I think a Japanese scientist named
See if they've got any in there.
the process of the.
And then there's what we call graupel, which is when a bunch of snowflakes are kind of stuck together. I can't find that. There's not one that I can think of that's has the word hand in it. There's whore. Could they have been talking about whore?
I forgot. I can check it next
Yeah.
time. I can tell you.
But there, in both of these books have, or at least this one definitely has a diagram of the different types of snow crystals. And some photographs. Yeah, here. So columns, needles, plates, stellar crystals or dendrites, irregular particles, graupel, hail. Could it have been hail that he was talking about?
I forgot.
Okay. And then ice pellets that all depend on different temperatures and humidity content. So thanks, Jürgen. That was good. All right, next.
Okay.
Okay.
Recording?
Yep.
Okay. How does the snow affect the atmosphere above it? That's our question. There's sorry.
It's okay.
There's two ways that we've noticed. They're readily apparent anyway. One is the insulating effect of the snow, which the air gets trapped under the snow, which is sort of obvious, I guess. I don't know. But the albedo effect of the snow actually traps the infrared radiating from the planet up. So there's a heat exchange that's being prevented by the snow.
Don't
I'm
worry.
terrible at this.
It's good practice.
This is why it's
I haven't done
practice.
this in years. Okay.
And I am gonna, on the first couple, I'm not gonna grade you quite as hard, but I will expect just
Improvement.
general improvements in confidence and all of that as we go on.
Yeah,
but
so I'll be better at this.
but you'll be.
Anyway,
This
okay.
is good practice.
What we may have noticed, what we noticed, and y'all may have noticed, is that the top layer of snow was very white. And the book touches on the albedo effect a bit more, but that usually means that the visual spectrum is being reflected. So it's a lot of energy that's being bounced right back into the air above the atmosphere. And the temperature effect might be, well, probably is negligible, but that could have a lot of interesting reactions with the actual the molecules and the clouds in the sky. Because a majority of the sun's energy is being reflected right off the snow back up in the air again. But we couldn't tell if it was the UV. Like the book doesn't go beyond 400 nanometers. And I guess the only way that we'd know to check that would be take a black light and shine it at the snow and see how much of it bounces off. But otherwise, I would assume that a lot of it is reflected as well. The important bit is the IR, though. Most of it from the sun is absorbed, but it varies with grain size, which means that the stuff in the sun is stopping just short of the surface, but again, the stuff on the planet, or from the ground, is not making it past the bottom layer as well. Large grains absorb most of the IR, which explains the large temperature difference as well, I would assume. So yes, the atmosphere is affected by basic heat robbing from the snow.
Okay, thank you.
What's IR?
That sounded a lot better in my head. Oh my god, I'm sorry. Infrared.
Oh,
Or
okay.
near infrared specifically.
It was good, but I would say you used a bit of jargon
Yeah.
but that's fine. This is why we practice this stuff, and
Minor anxiety.
and we will go into a lot more details on the albedo and that interaction, the long wave radiation, which is
Yeah, no, I actually had it in my head from the actual experiment that they did, not just from the book. But it's totally
cool.
like,
Yeah.
It's funny how just talking around the table like this, it's really easy to speak to the group, but then when you're standing,
Yeah, I don't know. Maybe it's just standing up, the light shining in your face and all.
Yeah.
Yeah, now you can actually see it too in the snow, like just the color itself, like the dark indicates the air is being absorbed.
Mm-hmm.
Okay.
But we didn't really go into that in the lab, so.
Yeah, we didn't talk about that too much, but
But we did take measurements of temperature. So.
we did take measurements of temperature. and there are plots, I'm sure, I don't know if it's in either of these books, but there have been measurements done on the wavelength of the light and how much is which ones are reflected more likely than others, both going to the shorter wavelengths, which are the ultraviolets, to the longer wavelengths, which are the infrared. So the infrared is the heat, ultraviolet is what gives us cancer, right? And in between is the visual. So, and snow is very reflective in the visual. There's details that you have to think about when you're up on the different ends of that wavelength spectrum in terms of the how reflective it is and what goes on with it. And it does affect the grain size. Does make a difference. So that's good. So, all right, next. Go. And there are I think I mentioned this to Amber, but there definitely are some ideas and concepts that are overlapping. So it's fine if when something that you say is a variation on something that somebody already else said. That's fine. It can help reinforce the ideas. So don't feel like you are repeating what somebody else just said, even if. Okay.
All right.
Go for it.
All right. My question is, how does the snow affect the ground underneath, and is the effect of the snow different at different times of the year? So, as the winter season progresses and the snow covers the ground more, the snow cover acts like an insulating layer. So basically what it does, it keeps the ground from heat loss, and this varies greatly with season, because during winter we can have the ground warmer than the top of the snowpack, but during autumn, when the snowpack is not as thick, it actually cools down the ground. And during spring, most of the solar radiation goes into melting the snow, so it doesn't heat up the ground, it cools it down. And another effect that snowpack can have on the ground is it can affect the permafrost. If the snow cover is more, it'll keep the ground warmer, so we might actually have loss of permafrost.
Okay, good. Cool. You stuck to the 60 seconds much better. No, it was good. Any questions you guys have?
Yeah, I was also working on this question.
Mm-hmm.
I was wondering, do the ground heat up all in spring before the snow is melted? Because I would think that the solar radiation are penetrating the snow and actually also heating the ground.
That's a good question. So yeah, if the ground were to heat up before the snowpack, then it would have to go through, because there's no heat source. The heat source under the ground is just the geothermal heat, which is the same all year round. Sunlight can get through 30 to 50 centimeters of snow, say. So there actually are animals that burrow in underneath the snow, and part of the reason that they're happily living under the snow is that there actually is some solar radiation that gets through. But
And also depth core plays a role in animals going through the snowpack.
The what? Sorry?
The depth core.
The depth core, yes. Because that sugar snow at the bottom, it's really easy for animals to burrow through that light snow. Yeah. Most of the radiation, though, that goes into the snow in the springtime, the first thing that it's going to try to do is warm up the snow itself. And so, yeah, so it's going to put all of its energy into warming up that snow. And actually, I think you had talked about this when I was talking with you over there, that the warming up of the ground is delayed because of that. So, and
the energy goes into melting of the snow, not the ground.
Yeah, and before it even can melt the snow, it has to warm it up. So, especially here in Fairbanks, where the snow is sitting there at -10, -20, depending on what's happening in March, as the sun comes out each day, it can warm it up a little bit, but then it cools off again at night. And so over the process there, it takes a while for it to, and it's called ripening of the snowpack, because it takes a substantial amount of time. I mean, last year we had snow on the ground until May, even though temperatures were above freezing for a month before that. And that's because it actually takes a long time to warm up that snowpack. And so you have to warm it up, and then you have to melt it. So just the warming up takes a long time, and then on top of that, the melting takes a long time. Whereas in a place like down in Washington, in the lower 48, where the snowpack over the whole winter is closer to that freezing point, once it does get warm, it can melt pretty quickly. So here we have quite a delayed melt because of the cold temperatures. Cool. Thank you. Do you have another question?
Does the snow pack over the season contribute towards like the compression of the ground at all as well? And would that affect the microbial activity? Which, I mean, that microbial activity plays some role in heating the ground as well. So, I mean, probably not here where there's permafrost, but
yeah, that's a good question.
Because there must be some biotic factor in that feedback.
There probably are.
But what would, like, how much would it actually amount to, though? Maybe
Probably.
the question up here.
Yeah, up here I think it's probably a lot different.
Mm-hmm.
I guess in lower latitudes it might be different.
It's a good
Wasn't
question
sure.
though, and since you weren't here on Thursday, and Ching, this is true for you as well, that if there is a certain aspect of the cryosphere that you're particularly interested in, like if the biological interactions are really interesting to you, then we can try to spend a little bit more time focused on them. Biology is not my expertise, but I'm happy to try to integrate it, because we'll talk about chemistry aspects of it, we'll talk about physics aspects of it, we'll talk about geology and sort of global geoscience aspects of it, and we certainly can bring in more of the biology if that's something that interests you. So, and if there's anything specific, I know Paul's doing stuff with isotopes in his research, so I know he's interested in isotopes of water and stuff like that. So, but if there's anything that you're interested in, let me know.
Talk to you about it later.
Yeah, or just definitely. The sooner you let me know, the more I can integrate it in if there's things that interest you.
Cool.
All right, Amber.
So my question was, what are the physical characteristics of the snowpack? How might they change when you change atmospheric conditions, make it warmer, or cause it to rain? So the snowpack that we observed was made up of several horizontal layers, beginning with a base layer of a dense, semi-transparent layer, and then sort of ascending into a less dense and culminating in a light and fluffy white layer at the top. If you were to increase the air temperature substantially, you could expect that the warming would cause the ice crystals to begin losing their edges and would begin to round and compact, thus becoming more dense. Similarly, if you were to saturate the snowpack with rain, for instance, it would fill all of the open air pockets within the snow and again compact them and become more dense.
Okay, good. That is good. Yeah, straight and to the point. And
That's all I got.
That's what I like. Yeah, so those were great, you guys, for your first kind of getting up and just going on. I do want you guys, I do want to keep track of time too. I think that was great. In the future, I think one thing that is common about all of you, and this is probably just the way everybody starting with announcing what your question was is probably okay for this particular assignment, but that's not something we would normally do in a presentation, right? So your message should already incorporate the idea that was in the question. And so that that's an effective way to start your presentation, may not be, depending on the situation, but usually it's not usually. This was a very. I gave you the questions to work with, but that's just something to think about. Like, can you integrate? Even though I gave you the topic, can you integrate the key things in that question into your presentation itself? And this is the same thing for anytime if you're given a topic. My topic is snow metamorphism. That's a rather dull introduction to a talk. If I got up there and said, I'm going to talk to you about snow metamorphism. So, which might be true, but is that always the best way to hook your audience and keep them interested in what you're doing? So I just noticed that you guys all did that, which is fine for today. It's not a big deal, but it's something to think about in the future as we get, as we practice these more and more. Because even though it is a little bit just like talking to each other and describing what we saw, the more you can practice making this like a real formal, not formal, but a real presentation, independent of just us discussing things, then that's more practice that you guys get in that. So